Hi, my name is Marco Lisi. I work for the European Space Agency and I was a former advisor of the European Commission on space policies. I am presently also advising the European GNSS Agency in Prague. I will speak in this lecture about EGNOS and Galileo, the two big programs of the European Union that are going to be the pillars of the European PNT infrastructure. Galileo, in a few words, is similar to GPS in principle, but it is using state-of-the-art technologies and concepts, and it will provide a very accurate and guaranteed positioning to not only Europe, but to the whole world, being under civilian control. It is meant from the beginning to be interoperable with other similar global navigation satellite systems such as GPS and GLONASS. In particular with GPS, the interoperability has been studied and agreed with the American authorities. So today there is a close cooperation between GPS and Galileo, and it will be like that also in the future. When the Galileo system will be fully deployed, it will consist of approximately 30 satellites. The core constellation is composed of 24 satellites. There will be some spares, either on ground or in orbit. And then there is the big and important ground infrastructure, the ground segment, that is somehow similar, as we'll see in a minute, to the EGNOS one. In terms of services, there is an open service that is open to all users, so there is no encryption of the signal, and this is similar to the open service presently provided by GPS. There will also be an encrypted type of service that in the case of Galileo is called the Public Regulated Service, PRS. This service is meant for government type of applications, and there will be a number of public organizations that might in the future take advantage of this system. It is very safe, secure, and reliable. And this is the reason also why the signals are encrypted. So you need to have a special code, to know the code to decrypt these signals. There is a search and rescue service. This is part of a larger organization that is the COSPAR-SARSAT organization around the world that is meant to provide search and rescue type of services, mainly for people in distress, in emergency situations, in case of maritime situations, or in any type of distress you might be. The commercial service is a real novelty of Galileo as compared to GPS. The idea here is to provide professional type of services, signals, that can be used by service providers in Europe and in the rest of the world to give value-added services to users. So it can further improve the capabilities and potentialities of Galileo. The integrity monitoring service that is being reprofiled is also meant to support safety of life, in particular aeronautical type of transportation applications. In this slide you see the architecture, in a very simplified way, the architecture of the Galileo system. You might recognize that it is similar to the EGNOS one we saw before. You have, of course, a constellation of satellites in orbit, which is important because it is the base for the system itself. But I would say the bulk of the complexity is in fact on ground. On ground you have a number of infrastructures, facilities, starting from the monitoring stations that are spread all over the world. In this case, they cannot be limited to Europe, they have to be everywhere in the world, and we'll see it later. They send their information to control centers, There are also 2 centers to follow the satellites in the very early stage of their life, when they are launched and they are put in the right orbit, and these are called LEOP, L-E-O-P centers. There are a number of stations that are instead linking to the satellites. Some are controlling the satellites themselves, these are called TT&C stations, and others are uplinking the navigation message, the one that is actually then broadcasted to users. There is also a center that is meant to measure the performance, continuously measure the performance of the satellites. Now, this big infrastructure that is spread in many centers in Europe and in the rest of the world is all connected by huge, very complex and reliable and secure communication network. So the overall infrastructure is very complex, and I wanted to stress the fact that it is a big information and communication technology type of system in itself. The Galileo program started many years ago, approximately around 2005, with 2 experimental satellites that were Jove A and B, that were meant to prove the feasibility of the system, but in particular some specific technologies, for instance, the atomic clocks. The Jove A and B satellites were launched in around 2005, and they were a big success, and they were operational, let's say, in terms of experiments for many years. Then in 2013, the so-called in-orbit validation phase started. This phase of the program is meant to prove the concept of Galileo at overall system level. The idea was to launch 4 satellites being the minimum, as we saw at the beginning of the presentation, to guarantee to be able to fix the position of a user, and to also develop the minimum ground infrastructure needed to provide this positioning. This phase has been concluded with success, and we'll see the results. Now we have already entered into the operational phase of Galileo, and we started launching the operational satellites. Then when we reach the full constellation, that will be around 2020, in a few years, and we have the full constellation in orbit and the full ground infrastructure developed, we'll be able to reach all the performance expected from Galileo. In this slide, you see the satellites of the IOV, the initial in-orbit validation phase. We positioned 2 satellites in one orbital plane, another 2 in another orbital plane. So the orbital planes of Galileo are 3. So with 4 satellites, we had to decide to put 2 on one orbital plane. And of course, not at all times and everywhere in the world you see the 4 satellites. In order to make a position fix, in other words, in order to be able to determine your location, you need to wait for the time when the 4 satellites are visible from the position you are in. Nevertheless, this minimum constellation of 4 satellites was enough for us to prove the concept of Galileo. And in this slide, you see instead how the IOV spacecraft looked like. The 4 first spacecraft of Galileo were developed by Astrium and integrated by Thales Alenia Space in Italy. They are not very big satellites. The spacecraft weighs approximately 700 kilograms, including the weight of the propellant. And it develops a total power of a bit less than 1.5 kilowatt, around 1400 watts. They are designed as the operational satellites spacecraft to last for 12 years. So they need to use very reliable components and technologies. You see in the picture the part of the satellite that is facing the Earth, and there are several antennas. The biggest antenna, we'll see in another picture later in another slide, is the so-called navigation antenna. Then at the bottom of the satellite you see the search and rescue antenna, and there are other antennas for the communication links to ground, TT&C and navigation message link. The technology on board the Galileo satellites is rather complex because it has to be very reliable, but it is not very new, but for some special components. One component I would like to focus our attention on are the atomic clocks. Atomic clocks are essential for navigation, satellite navigation systems, because as we saw at the beginning, it is the measurement of your position, the accuracy of your position fix. It's all based on the accuracy of the time reference you are using. So the satellites have to carry on board very precise clocks. On board the Galileo satellites, there are two types of technologies. One is relatively traditional, although it is difficult to make it space qualified, and it is about the rubidium clocks. A rubidium clock is very stable. It is so accurate that to accumulate an error of 3 seconds, you have to wait 1 million years. But there is an even better technology that is, for the first time, was developed in Europe and flown on board the satellite, that is the so-called passive hydrogen maser technology. And this is going to be even more stable than the rubidium clocks. It is as stable as to maintain an error of 0.5 nanoseconds, nanosecond being 1 billionth of a second, in 12 hours. Translated in terms of seconds, to accumulate an error of 1 second, you have to wait 3 million years. So these are very, very precise clocks. And it is all based, the accuracy of Galileo, it's all based on the precision, accuracy of the clocks. In the table that is in the slide, you see how an error in time translates in an error in a distance. If the speed of light is 300 million meters per second, so 1 second is an error, is equivalent to an error of exactly 300 million meters. 1 nanosecond, that is 1 billionth of a second, that is in fact more than, let's say, worse than the accuracy of the passive hydrogen maser, translates into 0.3 meters in terms of accuracy in this error in distance. Now in this slide, you can see the accuracy of the first position fix that was performed in March last year at ESTEC, ESTEC being the technical plant of the European Space Agency in the Netherlands. And you can see that with just 4 satellites and with a limited ground network, we were immediately able to achieve a good performance in terms of horizontal and vertical accuracy, approximately 6 meters in horizontal accuracy and 11 meters. You have to take into account that this was achieved with only 4 satellites, while the usual performance takes advantage of more satellites being visible and with a higher number of monitoring stations. So this was a very good, very first result. As I anticipated, we have to go for the full operational constellation, and this is going to be based on 24 satellites as a core constellation, plus some spares, and they will be put on 3 different orbital planes, 8 satellites on each orbital plane. In the slide here, you see an artistic view of the operational spacecraft that are produced by the German company OHB. And you see here the actual spacecraft being integrated at the OHB plant in Bremen. You see also you can compare the size of the spacecraft with the human figures that are close by. It is not a very big satellite and not a big spacecraft, but it is complex enough, and it's very important we have to produce many of them. So we have to set a sort of production capability. You see here another view where the antennas are very visible, in particular the biggest antenna, the circular antenna, is the navigation antenna. This antenna is manufactured in Italy by Thales Alenia Space. And at the bottom of the spacecraft you see the search and rescue, and at the top very small antennas that are there for communication links to ground. And in the following two slides you see some pictures of the production facilities where the operational spacecraft are produced, and of the qualification tests that are performed on the satellites. You can recognize, for instance, the vibration test on the satellites that are simulating the stress the spacecraft experience at launch, and also the thermal vacuum that reproduce the thermal conditions the spacecraft will experience in the space environment, in vacuum, and also some radiated tests that are checking the performance, the electromagnetic performance of the antennas and payloads.